Hello, and welcome to Space for Sleep. Venus is the closest true warning sign in the sky. It is not a distant icy giant, not a frozen moon, not an exotic world at the edge of the solar system. It is almost Earth's size. It is almost Earth's mass. It is made of the same basic rocky material. It formed next to us, around the same young sun, from the same original disk of gas, dust, metal, rock, and volatile compounds. And yet Venus became a furnace. Its surface is hot enough to melt lead. Its air is dense enough to crush machinery. Its clouds are made of sulfuric acid. Its atmosphere is almost entirely carbon dioxide. It has no oceans, no breathable air, no global magnetic shield, no surface refuge, and no visible landscape from space because the entire planet is hidden under a permanent reflective cloud deck. The disturbing part is not that Venus is strange. The disturbing part is that Venus is familiar. Venus is the most misunderstood planet in the solar system. From the outside, it looks almost identical to Earth. Same size, same mass, same density, same rocky composition. It formed at the same time, from the same cloud of gas and dust, in the same neighborhood around the same star. If you were designing a solar system and wanted to build a backup Earth, you'd probably build something that looks exactly like Venus. And yet Venus is a catastrophe. Its surface sits at 465 degrees Celsius on average, hotter than Mercury, despite being nearly twice as far from the Sun. Its atmospheric pressure is 90 times higher than Earth's at sea level, equivalent to the pressure you'd feel nearly a kilometer underwater in an ocean. Its clouds are made of sulfuric acid. Its atmosphere is almost entirely carbon dioxide. It rotates so slowly and in the wrong direction that a single Venusian day is longer than a Venusian year. It has no moon, no magnetic field, and no liquid water anywhere on its surface or in its atmosphere. Two planets, born side by side, from the same material around the same star. One became a world of blue oceans and breathable air and complex life. The other became the closest thing to hell in the solar system. Understanding how that happened and why is one of the most important questions in planetary science. Not just because Venus is scientifically fascinating, which it is, but because the answer directly concerns us. Venus is not simply a curiosity at the edge of human awareness. It is a mirror. It shows us what a planet can become when its climate loses control. It shows us what happens when the systems that regulate a world's temperature fail. And it sits 38 million kilometers away at its closest approach to Earth, close enough to see with the naked eye in the morning or evening sky, close enough that missions launched today can reach it in a matter of months. Venus is trying to tell us something. The question is whether we're paying attention. That is why Venus works so well as a scientific subject for an adult audience. It is not frightening because it is alien. It is frightening because it began so close to familiar. A small change in distance from the Sun, a different history of water, a different pattern of volcanic outgassing, a different rotation, a different ability to recycle carbon. From those differences came one of the most extreme surfaces in the solar system. This is also why Venus is not only a planet for astronomers. It belongs to climate science, geology, chemistry, atmospheric physics, and the study of exoplanets. It asks one of the deepest questions in planetary science. Why did two similar rocky planets, formed side by side, become so different? Earth became a planet where carbon dioxide could move between air, ocean, rock, and life. Venus became a planet where carbon dioxide accumulated in the atmosphere until the atmosphere itself became the dominant fact about the world. Earth developed a surface where liquid water can persist. Venus lost its water, and without water, it lost one of the main tools a rocky planet has for controlling its long-term climate. Earth has weather that changes the surface. Venus has weather that hides the surface. Earth has plate tectonics. oceans, and a biosphere. Venus has volcanic plains, sulfuric acid clouds, and pressure almost 100 times greater than ours. The comparison is not simple. Venus is not Earth's future in a direct or childish sense. Human-caused climate change is serious, but Earth is not about to become Venus. The physics of a true runaway greenhouse requires conditions that are not the same as the conditions facing Earth now. But Venus does show that climates have limits. It shows that habitability is not guaranteed by size, mass, or composition alone. A planet can look like Earth's twin in the table of planetary properties and still be completely incompatible with Earth-like life. That contrast gives the entire story its tension. Venus is bright in the sky, close in space, and almost impossible to survive on. It is familiar in bulk properties and extreme in environment. It is beautiful from a distance and lethal up close. It is one of the nearest planets to Earth, and for most of human history, we had no idea what was under its clouds. The clouds were the perfect disguise. They made Venus shine. They made it look clean, smooth, and reflective. They invited speculation about oceans and jungles. They turned the planet into a screen onto which people projected their hopes about life beyond Earth. But the same clouds that made Venus beautiful also concealed the evidence of its catastrophe. They hid the basalt plains. They hid the volcanoes. They hid the crushing lower atmosphere. They hid a surface where ordinary spacecraft die in hours. This is the correct way to approach Venus. Not as a romantic evening star, not as a simple warning label, but as a complete planetary system whose atmosphere, surface, interior, and history are locked together. The ancient world knew Venus without knowing what it was. The way Venus appears from Earth has also played an important role in the history of astronomy. Because Venus orbits closer to the Sun than Earth does, it never wanders far from the Sun in our sky. It is not visible at midnight high overhead like Jupiter or Saturn. It appears either before sunrise or after sunset, close to the horizon, bright enough to dominate the twilight. This geometry is the reason ancient cultures often treated it as two different objects before careful observation united the morning star and evening star into one planet. Through a telescope, Venus shows phases. Sometimes it appears nearly full and small. Sometimes it appears as a thin crescent and much larger. Galileo observed these phases in the early 17th century, and they became one of the strongest pieces of evidence that Venus orbits the Sun. In a purely Earth-centered system where Venus stayed between Earth and the Sun, the full range of phases would not make sense. In a Sun-centered system, the phases follow naturally. Venus therefore helped change not only planetary science, but the entire architecture of how humans understood the solar system. There are also transits of Venus, rare events in which the planet passes directly between Earth and the Sun, appearing as a tiny black disk crossing the solar face. These transits occur in pairs separated by 8 years, with more than a century between pairs. In the 18th and 19th centuries, expeditions were sent around the world to observe them, because precise timing of Venus transits from different locations on Earth could be used to calculate the scale of the solar system. The distance from Earth to the Sun, the astronomical unit, was one of the great measurements astronomers needed. Venus, bright and familiar in the sky, became a tool for measuring cosmic distance. That history matters because Venus has always been both obvious and hidden. It is easy to see with the naked eye. It is hard to understand physically. It helped prove the heliocentric system. It helped measure the solar system. It became a target for early spacecraft. And still, even now, many of its most important questions remain unanswered. The same planet that can be found by anyone in the twilight sky requires radar to map its surface, infrared observations to study heat escaping from below the clouds, ultraviolet imaging to reveal unknown absorbers, and atmospheric probes to measure the gases that carry its history. Venus looks simple only from far away. The closer science gets, the more complex it becomes. This is one of the reasons Venus is a strong subject for a long documentary script. It does not rely on one dramatic fact. It builds through contradiction. The planet is bright but hidden, similar to Earth but hostile, close but hard to explore, beautiful but lethal, familiar in the sky but unfinished in science. Each layer of the story reverses the first impression. To the naked eye, Venus is the brightest object in the night sky after the moon. It outshines every star, every other planet, every nebula or galaxy visible without a telescope. It can be bright enough, under the right conditions, to cast a faint shadow. Ancient observers saw it as two separate objects: the morning star that appeared before sunrise and the evening star that appeared after sunset, and for a long time didn't realize both were the same thing. The Babylonians identified Venus as a single object orbiting the sun and tracked its movements with remarkable precision more than 3,000 years ago. The ancient Greeks called the morning star Phosphorus and the evening star Hesperus before eventually recognizing them as one body and naming it Aphrodite. The Romans called it Venus after their goddess of love, and that name is the one that stuck. The Mayans built elaborate astronomical tables tracking Venus's movements and organized significant parts of their religious calendar around its appearances. Venus has been watched, recorded, and given meaning by human beings for as long as human beings have been looking at the sky. And yet for most of that history, what Venus actually was remained completely unknown. Because Venus is always covered by an unbroken layer of cloud, no optical telescope has ever seen its surface. Even with the most powerful Earth-based telescopes pointed at it, Venus shows only a featureless, gleaming, yellowish-white disk, clouds all the way down, no surface features, no shadows, no geography. For centuries, astronomers knew Venus was a planet roughly the size of Earth, and that was nearly everything they could determine from direct observation. Speculation filled the gap. By the 19th century, scientists were seriously proposing that Venus's thick clouds indicated a tropical atmosphere, that its surface might be covered in swamps and oceans, that it might support life, perhaps primitive plants, perhaps even animals. Carl Sagan, early in his career, briefly considered the hypothesis that Venus's clouds might contain organic chemistry produced by living organisms. The planet that humans had named after their goddess of love, it turned out, was also the planet onto which they had most consistently projected their own hopes and fantasies about inhabited worlds nearby. The correction, when it came, was dramatic. In the 1960s, a combination of Earth-based radio astronomy and then direct spacecraft measurements revealed that Venus's surface temperature was not tropical but lethal, that its clouds were not water vapor but sulfuric acid, that its atmospheric pressure was not manageable but crushing. The romantic vision of a lush, cloud-draped sister world was replaced in the space of a decade by something both more scientifically accurate and considerably more alarming. Venus had been hiding in plain sight, the brightest non-lunar object in the sky, for thousands of years, and it had been hiding a catastrophe. The basic physical facts of Venus matter before going any further, because they are remarkable in ways that are not always appreciated. Venus orbits the Sun at an average distance of about 108 million kilometers, compared to Earth's 150 million. This makes Venus the second planet from the Sun, sitting between Mercury and Earth. It takes Venus about 225 Earth days to complete one orbit. A Venusian year is shorter than an Earth year by about a third. But here is the first strangeness. A Venusian day is longer than a Venusian year. Venus rotates so slowly on its axis that it takes 243 Earth days to complete one rotation, which means that by the time Venus has completed a single rotation, One day, it has already completed more than one full orbit around the Sun. If you were standing on Venus's surface, you would experience a solar day, the time from one sunrise to the next, of approximately 117 Earth days. The Sun would rise, crawl almost imperceptibly across the sky over the course of weeks, and set 58 days after it rose. This is not just slow. It is the second slowest rotation of any planet in the solar system after Mercury, and the reason for it is not well understood. The leading hypothesis is that Venus was struck by a large object early in solar system history, an impact that significantly slowed its rotation and may have also reversed it. Because the second strangeness is this: Venus rotates backwards. Every other planet in the solar system, except Uranus, which is tilted on its side due to an ancient impact, rotates in the same direction. They all spin the same way the solar system originally rotated as it formed from a collapsing cloud of gas and dust. Venus rotates in the opposite direction. On Venus, the Sun rises in the west and sets in the east. If you could see through the clouds from Venus's surface, you would watch the Sun move in the direction that feels, from every other planet's perspective, wrong. This retrograde rotation has a number of consequences. Venus has no fast-spinning core to generate a magnetic dynamo, or at least, if it does have a molten iron core, that core is spinning too slowly, or in a way too different from the mantle, to generate a global magnetic field the way Earth's does. Venus has essentially no measurable intrinsic magnetic field. It has a very weak, induced magnetosphere created by the interaction of the solar wind with its atmosphere. But this provides almost none of the protection against solar wind erosion that Earth's magnetic field provides. The consequences of this for Venus's atmosphere, and specifically for its water, are significant and will return to them. The slow rotation has another less obvious consequence for the climate. It affects cloud formation. Some climate models suggest that if Venus rotated faster, even at a rate several times slower than Earth's, but far faster than its actual rotation, its cloud patterns might be dramatically different, with high-altitude clouds potentially forming over the subsolar point and reflecting enough sunlight to significantly reduce surface temperatures. This cloud feedback effect on a faster rotating Venus might have kept the surface cool enough for liquid water to exist even at Venus's solar distance. This is one of the lines of reasoning that suggests early Venus, if it rotated faster before a slowing event, might genuinely have been habitable. The rotation rate, in this scenario, was not just a curiosity, but a controlling variable in the planet's climate. Venus's diameter is about 12,100 kilometers, compared to Earth's 12,700, a difference of about 5%. Its mass is about 81% of Earth's. Its surface gravity is about 90% of Earth's. These are, by planetary standards, extraordinarily similar. If you fell asleep in a room on Earth and woke up in a room on Venus's surface, you would notice the gravity was slightly lower, but only if you were paying careful attention. Everything else about your situation would be immediately, terminally different, but the gravity, that fundamental measure of what a planet feels like underfoot, would be nearly the same. This similarity is why Venus is called Earth's twin, not because the two planets are remotely similar in any of the ways that matter for habitability. They are not, but because in the most basic physical parameters, mass, size, density, composition, they are the closest pair among the solar system's 8 planets. They are siblings who started with almost identical genetic material and ended up with completely different lives. Venus's orbit is also the most nearly circular of any planets. Its eccentricity, the measure of how elliptical rather than circular its orbit is only about 0.007, compared to Earth's 0.017. Venus moves around the Sun in almost a perfect circle. This means it receives almost exactly the same amount of solar energy at all points in its orbit, with no significant variation due to orbital distance. Whatever controls Venus's climate, it is not seasonal variation in solar energy input. The rotation problem is more important than it first appears. A planet's day length does not only determine how a sunrise looks. It affects atmospheric circulation, cloud formation, surface heating, interior dynamics, and possibly even the long-term ability of the planet to remain habitable. On Earth, a 24-hour rotation helps organize weather into familiar patterns. The Coriolis effect turns moving air, dividing the atmosphere into circulation cells, jet streams, cyclones, and trade winds. On Venus, the solid planet rotates so slowly that the surface barely turns beneath the atmosphere. But the atmosphere itself does not rotate slowly. At cloud top level, it whips around the planet in only a few Earth days. The result is a physical mismatch, a nearly motionless rocky world beneath a racing global atmosphere. That mismatch is one of the reasons Venus remains difficult to model. The air does not behave like a simple thick blanket. It superrotates. It transports heat from day side to night side with tremendous efficiency. It creates ultraviolet patterns that move and evolve. It forms waves that can be connected to mountains far below. It produces clouds that reflect most incoming sunlight, while at the same time helping trap the heat that turns the lower atmosphere into an oven. The retrograde rotation also raises a historical question. Did Venus always rotate this way, or did something happen to it? A giant impact is one possibility. Tidal interactions with the sun and atmospheric tides may also have played a role over billions of years. Venus is close enough to the sun that solar tides and thermal tides in its thick atmosphere matter. The atmosphere itself can exchange angular momentum with the solid planet. In such a system, rotation is not merely an initial condition. It is part of the planet's evolution. This matters for early Venus. Some climate models suggest that a slowly rotating Venus can build a thick reflective cloud shield on its day side, reflecting sunlight away and keeping the surface cooler than expected. Other models depend strongly on the amount of water, the composition of the early atmosphere, the brightness of the young sun, and the details of cloud physics. The result is not a single clean answer, but a range of possible histories. Venus may have been habitable for a long time, or it may have become hostile early. The current planet does not preserve enough surface evidence for us to know easily. That uncertainty is scientifically valuable. It means Venus is not a solved example. It is an active problem. Every mission that measures its atmosphere, surface composition, noble gases, isotopes, and volcanic history can help narrow the range of possible pasts. The slow backward rotation, which sounds at first like a strange trivia fact, becomes one of the clues in a much larger investigation. Venus also has no moon, one of only 2 planets in the inner solar system without one. Of the 4 rocky inner planets, Mercury and Venus alone are moonless. Earth's moon is thought to have formed from debris ejected by a giant impact early in Earth's history, and it has played a significant role in stabilizing Earth's axial tilt over geological time, helping maintain relatively consistent climate conditions across billions of years. Without a moon, Venus has no such stabilizer. Its axial tilt, currently very small, about 3 degrees, can in principle evolve over long timescales under the gravitational influence of other planets and the Sun, though the current tilt is so small that its effects on the planet's seasons are essentially negligible given how much larger the other climate forcings are. The atmosphere of Venus is where the story gets interesting and where most of what makes Venus Venus originates. The atmosphere is not only thick, it is vertically layered in a way that makes Venus feel like several different worlds stacked on top of one another. Near the surface, The air behaves almost like a supercritical fluid compared with the gases we are used to. Carbon dioxide under such high pressure is dense, hot, and efficient at transferring heat. The lower atmosphere does not allow night to bring meaningful cooling. It does not allow polar regions to escape the furnace. It smooths out temperature differences so thoroughly that the whole planet's surface remains nearly the same temperature, from equator to poles, from day side to night side. Higher up, conditions change dramatically. At 50 to 60 kilometers altitude, pressure and temperature pass through values that are surprisingly close to those at Earth's surface. This does not make the region friendly. The clouds are acidic. There is no breathable oxygen. The chemistry is aggressive. But in terms of temperature and pressure alone, the cloud layer is one of the most physically moderate environments beyond Earth. That is why Venus atmosphere platforms, balloons, and aerostats appear so often in mission concepts. Landing on the surface is brutally hard. Floating in the clouds is still hard, but it is a different kind of hard. This vertical contrast is one of the great ironies of Venus. The surface is more hostile than the surface of Mercury in some ways, but a layer of the atmosphere above it has temperatures and pressures that are easier to manage than the surfaces of Mars, Europa, Titan, or the Moon. A spacecraft in that cloud layer would not need to survive crushing pressure or lead melting heat. It would need to resist sulfuric acid, operate in strong winds, and communicate through a dense atmosphere. But it could in principle last much longer than any lander on the ground. The superrotation of the atmosphere makes that cloud layer even more interesting. A balloon drifting in the winds could circle the planet in a matter of days, sampling different longitudes, temperatures, cloud structures, and chemical environments without needing engines. The Soviet Vega balloons proved this in 1985. They were not science fiction. They actually floated in the Venusian atmosphere and returned data as they were carried around the planet. Future balloons could do far more, especially with modern instruments, better power systems, and relay orbiters. The cloud layer also matters because it is where many of Venus's chemical mysteries live. Sulfur dioxide rises from below, likely supplied by volcanism. Ultraviolet sunlight drives reactions above. Sulfuric acid droplets form and circulate. Trace gases appear and disappear. Unknown absorbers change how the atmosphere takes in solar energy. If there are missing chemical reactions in our models, they are likely hidden somewhere in this region, where light, acid, sulfur, chlorine, phosphorus, carbon dioxide, and tiny amounts of water interact. This makes Venus's atmosphere a laboratory for atmospheric chemistry under extreme conditions. It is not simply a carbon dioxide blanket. It is a dynamic chemical machine with layers, waves, winds, clouds, aerosols, and feedbacks. The surface furnace is the most dramatic result, but the machinery that maintains and modifies that furnace extends upward through the entire atmosphere. The Venusian atmosphere is enormous by any measure. Its total mass is roughly 90 times the mass of Earth's atmosphere, compressed into the same space around a similar-sized planet. At the surface, atmospheric pressure is about 92 bar, 92 times the atmospheric pressure at Earth's sea level. This is the pressure you'd experience at a depth of about 900 meters underwater in an Earth ocean. It's enough to crush a standard submarine. It's enough to kill a human being in seconds without any kind of protective suit, not from suffocation, not from temperature, but from the pure mechanical pressure of the gas itself compressing body cavities and tissues beyond any physiological tolerance. The composition of this enormous atmosphere is 96.5% carbon dioxide. Most of the remaining 3.5% is nitrogen, with trace amounts of sulfur dioxide, argon, water vapor, carbon monoxide, and a handful of other minor components. There is no free oxygen. There is almost no water. What water exists is present in parts per million, vastly less than exists in Earth's atmosphere. let alone Earth's oceans. The carbon dioxide concentration is the critical fact. Carbon dioxide is a greenhouse gas. It absorbs infrared radiation emitted by the surface and re-radiates it, trapping heat within the atmosphere rather than allowing it to escape to space. On Earth, carbon dioxide makes up about 400 parts per million of the atmosphere, less than 0.5% of 1%. This trace amount is enough to raise Earth's average surface temperature by several crucial degrees compared to what it would be without any greenhouse effect. Venus has 96% carbon dioxide, not parts per million, 96%. The difference in scale is difficult to overstate. The result is a runaway greenhouse effect. The incoming solar energy that reaches Venus's surface is absorbed and converted to heat. That heat is then trapped, not partially, not mostly, but almost completely, by the carbon dioxide atmosphere, which does not permit the heat to radiate back to space. The surface temperature reaches 465 degrees Celsius, hot enough to melt lead, hot enough to ignite wood, hot enough to cause copper to glow faintly in the dark. This temperature is maintained continuously, not just in afternoon, not just near the equator, not just in summer. At the poles, at the night side, at the highest latitudes, the temperature barely changes. The atmosphere is so thick and so efficient at trapping heat that it distributes that heat globally with extraordinary uniformity. The clouds of Venus, which are responsible for its brilliant appearance from space, are not made of water vapor. They are made primarily of droplets of concentrated sulfuric acid, formed from sulfur dioxide and water vapor reacting in the upper atmosphere under the action of solar ultraviolet radiation. These clouds exist in a deck that extends from roughly 45 to 70 kilometers above the surface, organized into multiple distinct layers with slightly different compositions and particle sizes. They reflect back to space about 70% of the sunlight that hits Venus, a reflectivity, called albedo, higher than any other planet. If Venus didn't reflect so much sunlight back to space, its surface would be even hotter than it already is. Above the cloud deck, Venus's atmosphere continues upward into a stratosphere and a thermosphere, with conditions becoming progressively less extreme as altitude increases. At cloud top altitude, around 60 to 70 kilometers above the surface, temperatures drop to approximately 0 to minus 40 degrees Celsius, and pressure drops to roughly the same as Earth's surface pressure. This region of Venus's atmosphere is, in terms of temperature and pressure, the most Earth-like environment anywhere in the solar system other than Earth itself. It is a fact that has not escaped the attention of mission designers, some of whom have proposed atmospheric habitats at this altitude as a way to maintain a human presence near Venus without ever having to deal with the lethal surface conditions. Below the clouds, the atmosphere clears somewhat, though it is never truly transparent. The lower atmosphere is dense, hot, and chemically aggressive. Sulfuric acid particles that descend from the cloud deck evaporate long before reaching the surface, where they be vaporized immediately by the heat. The surface is bathed in a diffuse, orange light, not sunlight in any recognizable sense, but a reddish-orange glow filtered through kilometers of thick atmosphere, giving Venus's surface an appearance somewhat like being inside a brick oven. The first Soviet spacecraft to survive long enough on Venus's surface to transmit images showed exactly this: an eerie, orange-lit landscape of flat rocks and boulders extending to a hazy, dim horizon, the sky above a uniform, featureless brownish-orange. Wind speeds in the lower Venusian atmosphere are actually relatively modest, around 1 to 3 kilometers per hour at the surface, which is less than a light breeze. But in the upper cloud layers, the winds are extreme, with jet streams reaching 360 kilometers per hour, circling the entire planet in only 4 Earth days. This phenomenon, called superrotation, means that Venus's atmosphere at cloud top altitude rotates 60 times faster than the planet itself rotates. The mechanisms driving this superrotation are still not completely understood and are one of the active research questions that future Venus missions hope to address. Venus also experiences lightning. The first evidence for Venusian lightning came from the Venera landers and then from Venus Express, which detected radio emissions consistent with lightning discharges in the cloud layers. Whether this lightning is similar in nature to terrestrial lightning, driven by charge separation in convective cloud cells, or operates through a different mechanism in Venus's sulfuric acid clouds is still being investigated. If Venus has active lightning on a significant scale, the lightning could be driving chemical reactions in the cloud layer that might help explain some of the unusual chemistry detected there, including, potentially, contributing to the phosphine puzzle we'll come to later. The chemistry of Venus's cloud layer is genuinely complex and not fully understood. The sulfuric acid clouds are not the only chemically active species present. Venus Express and earlier missions detected the presence of chlorine compounds, phosphorus compounds, and various sulfur species in the cloud layer, some of which react with each other and with the abundant sulfuric acid in ways that are still being mapped. Some of these reactions produce molecules that models predict should be present in the clouds but haven't been detected. Others produce apparent chemical imbalances, species that should be depleted by known reactions but appear in quantities larger than those reactions can explain. These imbalances might indicate missing chemical processes in the models, or they might indicate processes that we haven't yet fully characterized, or, in the most speculative interpretation, they might indicate the presence of chemistry that biology is driving. One atmospheric mystery that has received significant attention in recent years involves the unknown UV absorber in Venus's clouds. When Venus is observed in ultraviolet wavelengths, the cloud layer shows dark, streaky patterns, regions that absorb ultraviolet radiation much more strongly than pure sulfuric acid would. Something in the cloud layer is absorbing UV, and we don't know what it is. The absorber exists primarily in the upper and middle cloud layers, where it produces the visible markings that give Venus's cloud system its distinctive striped and patchy appearance in UV images. Various chemical candidates have been proposed: iron chloride, allotropes of sulfur, ammonium bisulfate, and others, but none has been confirmed as the primary absorber, and the possibility that it might be something biological has never been entirely ruled out. The amount of solar energy absorbed by this unknown UV absorber is not negligible. It accounts for a significant fraction of the total solar energy absorbed by Venus's cloud layer, which means that whatever it is, it has a real influence on the energy balance of Venus's atmosphere. And understanding it is not just a matter of curiosity, but of understanding how Venus's climate system works at a fundamental level. Venus did not become this world because of one simple switch being thrown. It became this world through planetary evolution, a long, physical chain of heat, water loss, atmospheric chemistry, volcanic outgassing, solar radiation, and failed climate regulation. It may have happened gradually across hundreds of millions of years. It may have crossed one or more thresholds suddenly by geological standards. It may have involved both slow drift and catastrophic transitions. Understanding the greenhouse effect on Venus requires understanding it on Earth first, because the same physics operates on both planets. The Sun emits radiation across a range of wavelengths, with the peak in the visible light range. Earth's atmosphere is largely transparent to this visible light, which passes through and warms the surface. The warm surface then re-radiates energy at longer, infrared wavelengths. Greenhouse gases in the atmosphere, primarily water vapor, carbon dioxide, and methane, absorb this infrared radiation rather than letting it pass directly to space and re-emit it in all directions, including back toward the surface. This trapping of infrared radiation is what raises the surface temperature above what it would be with no atmosphere. On Earth, this process is carefully balanced. The amount of greenhouse gas in the atmosphere, the reflectivity of the surface, the behavior of water, the role of biology in cycling carbon, all of these factors interact to maintain temperatures in a range that, while variable over geological time, has remained compatible with liquid water and complex life for billions of years. On Venus, the balance was disrupted, or was perhaps never properly established to begin with. The most dangerous part of the greenhouse effect is not that it exists. On Earth, it is necessary. Without greenhouse warming, Earth's average surface temperature would be far below freezing, and the planet would not have the stable surface oceans that make complex life possible. The issue is not greenhouse physics itself. The issue is feedback. A feedback is a process that either dampens a change or amplifies it. On Earth, several negative feedbacks help stabilize climate over long timescales. When temperatures rise, chemical weathering of silicate rocks can accelerate, drawing carbon dioxide out of the atmosphere and eventually locking it into carbonate minerals. When temperatures fall, weathering slows, volcanic carbon dioxide can accumulate, and the climate can warm again. This is not a thermostat in the mechanical sense. It is slow, messy, and affected by biology, geography, ocean chemistry, and tectonics. But over geological time, it has helped keep Earth within a range where liquid water can persist. Venus lost the conditions that make such regulation possible. Without surface water, chemical weathering is crippled. Without oceans, carbon dioxide cannot be efficiently dissolved, transported, and buried. Without Earth-like plate tectonics, carbon-bearing rocks are not recycled in the same steady way. If volcanoes continue to release gases while the main removal pathways fail, the atmosphere becomes a one-way reservoir. Carbon enters. Very little leaves. This is why Venus is a climate problem as much as an astronomy problem. Its atmosphere is not just thick, it is the historical record of failed carbon regulation. Every bar of pressure, every molecule of carbon dioxide, every trace of sulfur dioxide, every isotope ratio in the air carries information about the planet's past. The atmosphere is a kind of archive, but not one written in layers like sedimentary rock. It is written in composition. Noble gases are especially important here. Elements such as argon, neon, krypton, and xenon do not react easily with rocks or clouds. Their abundances and isotope ratios can preserve clues about how Venus formed, how much atmosphere it lost, how much material was delivered by comets and asteroids, and how its volcanic outgassing history compares with Earth's. This is one reason Da Vinci's measurements matter. A descent probe moving through the atmosphere can measure noble gases directly and help decide between competing histories. Water isotopes matter as well. The high deuterium to hydrogen ratio in Venus's atmosphere tells us that ordinary hydrogen escaped more easily than heavier deuterium. That is a fingerprint of water loss. But the fingerprint does not tell the whole story by itself. It does not tell us exactly how much water Venus began with, how long it remained, whether it pooled into oceans, or whether it was mostly atmospheric steam. To answer those questions, scientists need atmospheric measurements, surface geology, models of early solar radiation, and better understanding of Venus's interior. The runaway greenhouse story is therefore not a slogan. It is a sequence of linked physical processes. Solar energy warms the planet. Water vapor amplifies warming. Ultraviolet light breaks water apart. Hydrogen escapes. Oxygen reacts away. Carbon dioxide accumulates. Oceans, if they existed, vanish. Weathering stops. Volcanism continues. The atmosphere grows heavier and more heat-trapping. Eventually, the surface becomes a stable furnace, not because it is balanced in a life-friendly way, but because it has locked into a different kind of equilibrium, hot, dry, dense, and almost impossible to reverse. That is the real horror of Venus. Not that it is changing rapidly now, but that it changed so completely that the present world is locked into its state. It is a planet after the loss of its escape routes. The dominant theory for how Venus ended up in its current state involves a concept called the runaway greenhouse effect. In this scenario, a planet receives enough solar energy that, if temperatures rise above a certain threshold, the resulting increase in atmospheric water vapor being itself a potent greenhouse gas, traps enough additional heat to raise temperatures further, which puts more water vapor into the atmosphere, which traps more heat, which raises temperatures further, in a self-reinforcing cycle that does not reach a stable equilibrium. The process continues until all surface water has evaporated into the atmosphere, at which point ultraviolet radiation from the sun breaks the water molecules apart, the hydrogen escapes to space, and the oxygen reacts with surface rocks. The planet is left with a desiccated, ultra-hot surface and an atmosphere consisting of whatever was left over. In Venus's case, primarily the carbon dioxide that was already there and the carbon dioxide outgassed from volcanic activity over billions of years. Whether Venus experienced a true runaway greenhouse effect, the kind that proceeds irreversibly once started, or a slower, more gradual drying out, is a question that planetary scientists are actively working to answer. The distinction matters because it affects how similar Venus's early conditions might have been to Earth's, and how easily a planet in Venus's orbital position could transition from habitable to uninhabitable. Venus is closer to the Sun than Earth, and receives about 1.5 times as much solar energy. Current models of planetary habitability suggest that Venus sits very close to the inner edge of the habitable zone, the region around a star where liquid water can exist on a planet's surface. Some models place Venus just inside the inner edge. Others suggest that early in solar system history, when the Sun was about 30% less luminous than it is today, Venus may have been within the habitable zone. If the early Venus had less carbon dioxide in its atmosphere, more reflective clouds, or a faster rotation rate that helped distribute heat more evenly, it may have maintained temperatures compatible with liquid water for a significant period. We don't know how long that period might have been. We don't know whether liquid water ever existed on Venus's surface in any substantial quantity, or whether the planet was always too warm for it. The geological record that might answer this question is almost completely inaccessible, because Venus's surface is geologically young by planetary standards, and whatever record might have been preserved in older rocks has almost certainly been erased by the volcanic and tectonic activity that has resurfaced the planet in the relatively recent geological past. What we do know is this: the carbon dioxide concentration in Venus's atmosphere today represents an enormous accumulation, the result of billions of years of volcanic outgassing without the recycling mechanisms that exist on Earth. On Earth, carbon dioxide is constantly being cycled out of the atmosphere through chemical weathering of silicate rocks, through dissolution in the ocean, and through biological processes. This carbon ends up locked in carbonate rocks on the seafloor, and is eventually returned to the atmosphere through volcanic activity when those rocks are subducted into the mantle and their carbon is released again. This carbon silicate cycle acts as a planetary thermostat, regulating atmospheric carbon dioxide concentration over geological timescales and helping maintain temperatures in a range compatible with liquid water. Venus has no oceans. Without oceans, the carbon silicate cycle cannot operate in the same way. Carbon dioxide emitted by volcanoes has no effective sink, no ocean to dissolve in, no mechanism to lock it into seafloor sediments, no reliable way to remove it from the atmosphere on geological timescales. It simply accumulates. Over billions of years, The carbon dioxide outgassed from Venus's interior has built up to the crushing atmospheric concentration we observe today. Whatever feedback mechanisms might have moderated Venus's early climate, they were eventually overwhelmed, and the planet crossed a threshold from which there is no return without massive intervention. There is also a psychological trap in the comparison between Earth and Venus. Because Venus is so extreme now, it is tempting to treat its outcome as inevitable, as if the planet was always doomed simply because it was closer to the Sun. But inevitability is exactly what scientists are trying to test. If early Venus had water, clouds, and a slower solar input under the faint young sun, it may have spent a long time in a state that was not obviously doomed. It may have had seas, or shallow oceans, or transient wet regions, or a steam-rich atmosphere that never fully condensed. Different models produce different worlds. Some are habitable for long periods. Some lose water quickly. Some depend strongly on rotation. Some depend on the initial inventory of carbon dioxide. The range of possibilities is wide because the evidence is incomplete. This uncertainty is not a weakness of Venus science. It is the reason the planet is worth returning to. A solved planet would not need Da Vinci, Veritas, and Envision. Venus needs them because the key evidence is still missing. Noble gases can reveal formation and escape history. Surface composition can hint at past water-rock interaction. Radar can show whether the crust is actively deforming. Infrared emissivity can suggest differences in rock type. Atmospheric chemistry can reveal whether volcanoes are adding gases now. Every measurement narrows the possible past. For adult viewers, this is the deeper hook. Venus is not only spectacular, it is unresolved. The story is not Venus is hot, and then a list of numbers. The story is Venus should have been the planet most like Earth, and we still do not know exactly when and how it stopped being that. That question has enough tension to carry an entire episode because it connects every scientific section: rotation, clouds, water loss, volcanism, surface geology, atmospheric chemistry, and future missions. A good Venus script should therefore keep returning to the divergence, not in a repetitive way, but as the central thread. Earth and Venus begin close together. They separate. Each fact explains part of the separation. Carbon dioxide explains heat. Water loss explains failed regulation. Volcanism explains atmospheric supply. No plate tectonics explains weak carbon removal. Clouds explain visibility and albedo. Mission history explains why we still do not know enough. The planet becomes not a random collection of facts, but a case study in planetary fate. Earth sits on the other side of that threshold, just barely. The margins that kept Earth habitable, the distance from the sun, the presence of oceans, the evolution of plate tectonics that enables the carbon silicate cycle, the eventual development of photosynthetic life that began removing carbon dioxide from the atmosphere, were real, but they were not large. Venus is a reminder of how the same starting conditions, offset by a relatively modest difference in solar energy input or an early difference in atmospheric composition or water inventory, can produce outcomes that are not merely different, but diametrically opposite. The surface of Venus is hidden beneath its clouds, and for most of human history, that was that. No telescope could see through the cloud deck. No surface detail was visible. The planet that dominated the evening sky was, geologically, a complete blank to human science. Radar changed everything. Radar maps do more than reveal shapes. They reveal a planet whose geology is both familiar and deeply strange. The familiar part is volcanism. Basalt plains, shield volcanoes, lava channels, calderas, and rift zones all point to a rocky planet with a hot interior and a history of magma reaching the surface. In that sense, Venus belongs with Earth, Mars, Mercury, and the Moon. It is a solid world where heat escapes from the interior through crustal deformation and volcanic activity. The strange part is the style. Venus does not show the global plate boundaries that make Earth's geology so readable. There are no ocean basins being created at mid-ocean ridges. There are no long trenches where plates dive back into the mantle. There are no continents moving across the globe in the Earth-like sense. Instead, Venus has a stagnant or sluggish lid, broken and deformed in places, pierced by volcanism, folded into highlands, stretched into rifts, and marked by coronae that look like scars from mantle upwellings pressing against the crust from below. This makes Venus a possible window into early Earth. Before modern plate tectonics became established, Earth may also have passed through stages of stagnant lid or episodic lid behavior, where heat escaped in pulses rather than through continuous plate recycling. Because Earth's surface is constantly renewed by plate tectonics and erosion, much of that ancient record is gone. Venus, despite being hostile, may preserve clues about forms of rocky planet evolution that Earth experienced and then erased. The tesserae are especially important. These heavily deformed highland regions may be among the oldest surfaces on Venus. If any rocks preserve evidence of earlier climate, earlier crustal composition, or possible interactions with water, the tesserae are among the best places to look. This is why Da Vinci's descent imaging of Alpha Regio matters. Even if the probe does not land and survive for long on the surface, images and composition measurements during descent could help reveal whether these ancient highlands are made of basalt like the plains or something more silica-rich, perhaps more like continental crust on Earth. That question is enormous. On Earth, continental crust is strongly linked to water and plate tectonics. It is lighter, more silica-rich, and chemically distinct from the basaltic oceanic crust. If Venus has large regions of non-basaltic crust, it could imply a more complex geological history than a simple volcanic plains planet. It could hint at processes that required water or at least a different melting history. If the tesserae are basaltic, that would tell a different story. Either answer matters. Venus's impact craters also reveal the power of the atmosphere. Small meteoroids never reach the ground because the dense air destroys them. The craters that do exist tend to be larger, often modified by the atmosphere, sometimes surrounded by radar-bright ejecta patterns. Their distribution helped scientists estimate the surface age. The fact that craters are not heavily clustered in one ancient region and absent in another supports the idea that much of the surface was reset within the last billion years. But reset does not necessarily mean the whole planet was resurfaced in one single global lava catastrophe. Some modern interpretations favor more gradual, regional, or ongoing resurfacing. Venus may not be a planet that sleeps for hundreds of millions of years and then erupts everywhere at once. It may be more continuously active, with volcanism, coronae, and deformation reshaping regions over time. The recent evidence for active volcanism strengthens that view. A future radar orbiter will be able to test this directly. If Veritas or Envision maps the same regions that Magellan mapped and sees changes, those changes could reveal fresh lava flows, shifting volcanic vents, landslides, or surface deformation. For Venus geology, repeat imaging is the difference between looking at a photograph and watching a planet move. Radio waves at certain wavelengths penetrate Venus's cloud cover, bounce off the surface, and return to the source in ways that allow the surface topography to be mapped. Beginning with Earth-based radar studies in the 1960s and 1970s, and culminating in NASA's Magellan spacecraft, which orbited Venus from 1990 to 1994 and mapped nearly the entire surface with synthetic aperture radar, scientists assembled the first comprehensive picture of what lies beneath the clouds. What the radar revealed was a world unlike any other in the solar system. Venus's surface is dominated by lowland volcanic plains covering roughly 80% of the planet's surface area. These plains are made of basaltic lava, dark, dense volcanic rock similar in composition to the basalt that forms Earth's ocean floors and volcanic islands like Hawaii. The plains are relatively smooth over large scales, but textured on smaller scales with lava flows, volcanic features, and impact craters. The paucity of impact craters. Venus has far fewer craters than the Moon or Mars, tells us that the surface is geologically young. Most estimates put the average age of Venus's surface at between 300 million and a billion years, meaning the surface has been substantially reshaped by geological activity within that period. Venus has no plate tectonics in the Earth sense. On Earth, the crust is divided into a series of large, rigid plates that move relative to each other, colliding to form mountain ranges, pulling apart to form ocean basins and mid-ocean ridges, and subducting into the mantle at deep ocean trenches. This continuous process recycles the crust, delivers carbon-bearing rocks into the mantle where their carbon is returned to the atmosphere, and provides the mechanism for the carbon silicate cycle. Venus appears to have a one-plate planet, a thick, stagnant lid of crust sitting over a hot, convecting mantle with no large-scale lateral motion of the kind that defines plate tectonics. This has several consequences. Without subduction, there is no way to recycle surface crust into the mantle and bring fresh mantle material to the surface in the systematic way that mid-ocean spreading does on Earth. Without the carbonate silicate cycle operating through oceanic crust, there is no long-term carbon regulation. And without the systematic pressure relief that subduction provides, the mantle heat may build up periodically until a catastrophic global resurfacing event, a planet-wide volcanic upheaval that essentially turns the surface inside out, releasing an enormous amount of carbon dioxide and lava simultaneously before a new stagnant lid forms and the cycle begins again. This episodic resurfacing hypothesis is one way of explaining the relatively young age of Venus's surface and the relative uniformity of that age. The geological record suggests the current surface formed more or less simultaneously across the planet, rather than in the piece-by-piece fashion that would result from steady, ongoing plate tectonic activity. The most recent global resurfacing may have occurred somewhere between 300 million and 700 million years ago. It may happen again on some future geological timescale when the internal pressure builds high enough. Scattered across the volcanic plains are upland regions called terrae, a Latin word meaning lands. These highlands are the oldest features on Venus's surface, and they include the two most prominent continental-scale uplands. Ishtar Terra, in the northern hemisphere, is roughly the size of Australia and is characterized by a high plateau called Lakshmi Planum, surrounded by mountain ranges. Maxwell Montes, the highest mountain range on Venus, rises to about 11 kilometers above the average surface elevation, roughly the same height above the Venusian baseline as Mount Everest rises above Earth sea level. Maxwell Montes is thought to be a fold mountain belt formed by compressional forces, the terrain being crumpled and pushed upward as subsurface material moves laterally, similar in principle to the process that built the Himalayas on Earth, though through different mechanisms. Aphrodite Terra, the other major highland region, straddles the equatorial zone and is roughly the size of South America. It contains some of Venus's most rugged terrain, including long, linear ridge belts and deep rift valleys, suggesting that this region has experienced extensional tectonics, the crust being stretched and pulled apart rather than compressed. Between and around these highland regions, the volcanic plains are punctuated by thousands of volcanic features of various kinds. Some are large shield volcanoes, broad and gently sloping, similar in form to Hawaiian volcanoes on Earth, built up by repeated eruptions of relatively fluid basaltic lava. The largest of these, Mont Mons, rises about 8 kilometers above the surrounding plains and is one of the most prominent volcanic features on the planet. Others are stranger features with no clear Earth analog. Coronae, singular, corona, are circular or oval-shaped structures, typically ranging from a few hundred kilometers to a few thousand kilometers in diameter, formed by plumes of hot material rising from the mantle below, doming the surface upward and then collapsing partially as the plume cools or moves, leaving behind a distinctive ring of fractures and ridges. There are hundreds of coronae on Venus, and they are found nowhere else in the solar system. Arachnoids, named for their resemblance to spiders, are circular features surrounded by complex networks of fractures radiating outward from a central region, again unlike anything seen on other planets. Tesserae, sometimes called tile terrain, are regions of highly deformed, complex terrain with multiple intersecting sets of ridges and valleys, thought to represent some of the oldest surviving portions of Venus's crust, existing before the most recent episode of volcanic resurfacing. This geological variety tells us that Venus's interior is still hot, still active, still generating enough heat to drive volcanic and tectonic processes at the surface. But it's worth pausing here to try to make the scale and character of this landscape tangible, because Venus's surface is so unlike any environment in human experience that it resists easy imagination. Imagine standing on Venus's volcanic plains. The gravity is about 90% of Earth's, so movement would feel only slightly different from walking on Earth. The ground beneath you is dark basaltic rock, often fractured and angular, the surfaces of lava flows that cooled decades or centuries or millennia ago. In some directions, the plain extends to a hazy horizon about 2 to 3 kilometers away, the same angular distance as on Earth, roughly, because Venus is a similar size. In other directions, you might see the low dome of a volcanic shield rising perhaps a kilometer or two from the surrounding plain, its flanks obscured by the thick, reddish haze of the lower atmosphere. The sky above is a uniform, featureless brownish-orange. There is no blue. There is no visible sun. The cloud deck, 45 kilometers above you, diffuses the sunlight into a bright, sourceless glow that comes from no particular direction and casts no shadows. The light level is roughly equivalent to a heavily overcast day on Earth, dim but not dark enough to see by, but giving the landscape a flat, unvaried quality without shadows. The temperature is 465 degrees Celsius. At that temperature, lead is liquid, tin is liquid, zinc is liquid. Most plastics would long since have vaporized. Standard steel alloys would still be solid, but many softer metals would not. The rock beneath you radiates heat you cannot feel because nothing that could feel it could exist there long enough to experience it. The air itself, the dense, carbon dioxide air pressing down at 92 times the pressure of Earth's atmosphere, carries that heat in every molecule, pressing against any structure you can imagine with a force equivalent to nearly a kilometer of ocean. The Soviet Venera landers, the only human-made objects to have survived on Venus's surface, lasted between 23 and 127 minutes before the combination of heat, pressure, and chemical corrosion destroyed them. They were built specifically to survive as long as possible, designed with thick pressure vessels, thermal insulation, and cooling systems, built in the 1970s and 1980s with the best engineering available at the time, aimed at a single goal: surviving on Venus for long enough to transmit useful data. 127 minutes was the best anyone has ever managed. Future missions aimed at surviving longer face an engineering challenge unlike almost anything else in planetary science. The electronics and sensors that spacecraft rely on stop functioning reliably above about 125 degrees Celsius. Standard commercial electronics fail well before that, and even specially hardened electronics struggle above about 300 degrees. At 465 degrees, essentially all conventional electronics fail. Some research groups are developing electronics based on silicon carbide and other high-temperature semiconductor materials that could potentially operate at Venusian surface temperatures, but this technology is still maturing and has not yet been deployed in a surface mission. One concept that has been proposed involves a wind-powered clock approach, a mechanical, clockwork-driven lander that relies on Venus's surface wind and does not need electronics at all, using mechanical actuators to control instruments and transmit data as mechanical signals to a relay spacecraft overhead. This concept, developed at NASA's Jet Propulsion Laboratory, represents an attempt to use 19th-century engineering principles to solve a 21st-century planetary exploration problem. Whether it will ever fly depends on funding and priority decisions that are still being made. The evidence for current volcanic activity on Venus has been building for years, and the argument is now more compelling than it has ever been. In 2010, analysis of data from the European Space Agency's Venus Express mission, which orbited the planet from 2006 to 2014, found localized hotspots in the infrared, regions of the surface that appeared significantly warmer than their surroundings. These hotspots were associated with known volcanic features, and their temperatures were consistent with fresh lava flows, volcanic calderas, or other active geological processes. The data were intriguing but not conclusive. In 2023, a more definitive result appeared from the same Venus Express dataset. Researchers re-examining archival radar images and infrared data found direct evidence of a volcanic vent changing shape over an 8-month period in 2008 and 2009. The vent, associated with Mont Mons, appeared to expand from a circular opening to a more irregular, flooded shape, consistent with fresh lava filling and partially collapsing the vent structure. Combined with the thermal anomalies detected nearby, this was the strongest evidence yet that Venus is volcanically active today, not just geologically recently. Further support has come from analyses of Venus's atmospheric chemistry. Sulfur dioxide, a gas associated with volcanic emissions on Earth, is present in Venus's atmosphere in concentrations that models suggest should decrease over time as the gas reacts with surface rocks and cloud droplets unless it is continuously replenished by volcanic outgassing. The persistence of sulfur dioxide at measured concentrations implies an ongoing source, which is most naturally explained by current volcanism. If Venus is indeed actively volcanic today, and the evidence increasingly suggests it is, then its surface is continuously being modified by eruptions, lava flows, and volcanic outgassing. This makes Venus not a geologically dead world of ancient, frozen geology, but an ongoing, dynamic, geologically active planet whose interior processes are still shaping its surface in real time. It also means that any mission landing on Venus's surface needs to be aware that it is operating in a geologically active environment where conditions could change. The volcanic activity has another important implication. It is one of the primary mechanisms by which carbon dioxide is continuously pumped into Venus's already saturated atmosphere. Every volcanic eruption on Venus releases carbon dioxide from the mantle into an atmosphere that already has almost no capacity to absorb it. There is no ocean to dissolve it, no weathering process removing it at a rate comparable to its input. It simply adds to the crushing burden already present. Venus's volcanism is, in effect, adding fuel to a fire that has been burning for billions of years. The evidence for volcanism is important because Venus's atmosphere and surface cannot be understood separately. A volcano on Venus is not merely a mountain with lava. It is a connection between the deep interior and the climate system. On Earth, volcanic gases enter an atmosphere that is oceans, rain, weathering, biology, and plate tectonics. Carbon dioxide released by volcanoes can eventually be removed by reactions with rocks and stored in carbonate minerals. Sulfur gases can become aerosols and fall out through precipitation. The system has pathways for both addition and removal. On Venus, the removal side is much weaker. Volcanic gases enter an atmosphere already dominated by carbon dioxide and sulfur chemistry. There is no rain at the surface. There are no oceans. There is no biosphere drawing gases into living systems. The atmosphere can process sulfur compounds in clouds, and surface reactions can occur, but the global regulatory machinery is not Earth-like. This means volcanism on Venus may have had a much larger and more permanent climatic consequence. Active volcanism also affects the phosphine debate, the sulfur dioxide cycle, and the unknown chemistry of the clouds. If volcanoes inject phosphorus-bearing compounds, sulfur gases, chlorine compounds, or fresh aerosols into the atmosphere, they may create chemical pathways that are missing from simpler models. A gas that looks mysterious from a distance may not require biology if the planet's geochemistry is more active or more unusual than assumed. The 2023 and 2024 reanalyses of Magellan data were especially important because they turned Venus volcanism from a plausible inference into something closer to direct geological evidence. Scientists could compare radar images taken at different times and identify changes consistent with new lava or a changing volcanic vent. That is the kind of evidence planetary geologists value, not just a volcano-shaped mountain, but a surface that changed while a spacecraft was watching. The implication is striking. Venus may be volcanically active on a scale comparable in some ways to Earth. Not Earth-like in tectonic style, not Earth-like in climate, but active enough that the idea of a dead Venus is no longer reasonable. Its surface may be renewing, cracking, erupting, and deforming under the cloud cover right now. That changes the emotional character of the planet. Venus is not simply a fossil of a failed climate. It is a living geological system without life. Hot interior, moving mantle, erupting lava, deforming crust, circulating atmosphere, evolving clouds. The catastrophe is not static. It is maintained by ongoing planetary processes. For a future mission, this is exciting and difficult. It means that a radar orbiter could catch changes. It means infrared instruments might detect fresh lava or warm surfaces. It means atmospheric probes could measure volcanic gases and connect them to active regions. It means a long-lived balloon might detect pressure waves or chemical signatures from eruptions below. The planet is not just waiting to be mapped. It may be doing things while we watch. Water is the story underlying much of what happened to Venus. Understanding where Venus's water went and how it was lost is central to understanding why the two planets diverged so dramatically. Earth has abundant water. Roughly 70% of Earth's surface is covered by oceans, with average depths of about 3.5 kilometers. In addition to surface water, water is present in the atmosphere, in groundwater, in ice sheets, in the water of crystallization within rocks. Water is central to virtually every major geological, chemical, and biological process on Earth. Its presence has, over geological time, been essential to maintaining the carbon-silicate cycle, driving plate tectonics, and making the planet habitable. Venus, today, has almost no water. The trace amounts of water vapor in Venus's atmosphere represent a total water inventory that is, by any estimate, orders of magnitude smaller than Earth's. Where did it go? The answer, almost certainly, is that Venus's water was destroyed, broken apart by ultraviolet radiation from the sun, and then lost to space. The process works like this. Water molecules in the upper atmosphere are exposed to ultraviolet radiation from the sun, which is energetic enough to break the molecular bonds holding hydrogen and oxygen together. The water molecule dissociates, releasing individual hydrogen and oxygen atoms. Hydrogen atoms are extremely light, the lightest element in the universe. and at the temperatures found in Venus's upper atmosphere, a significant fraction of them move fast enough to exceed Venus's escape velocity and be lost to space entirely. The oxygen atoms left behind react with surface minerals or other atmospheric gases, becoming locked into less mobile chemical compounds. Over time, this process, called photodissociation followed by hydrodynamic escape, can drain a planet's water inventory entirely. On Earth, this process is slowed dramatically by two factors. First, Earth's atmosphere has a cold trap, the tropopause, a region where temperatures are low enough that most water vapor condenses and freezes before reaching altitudes where it would be exposed to significant ultraviolet radiation. Most water is locked out of the upper atmosphere by this freezing trap, reducing the rate at which it can be photodissociated and lost to space. Second, Earth's magnetic field deflects much of the solar wind that would otherwise enhance the escape of atmospheric gases, providing a protective envelope that helps retain the atmosphere. Venus has neither of these protections in the same form. Its cold trap is less effective because Venus's lower atmosphere is so hot. Water vapor can be mixed upward to high altitudes where it is exposed to ultraviolet radiation more readily than on Earth. And without a significant magnetic field, Venus has no defense against the solar wind, which strips atmospheric gases from the upper atmosphere at an enhanced rate. Over billions of years, these two factors working together could have removed all of Venus's original water inventory. The rate at which Venus is losing hydrogen today, measurable by spacecraft instruments in the upper atmosphere, is consistent with this picture. Venus Express measured the hydrogen escape rate and found it consistent with Venus having lost an ocean's worth of water over the lifetime of the solar system. Whether that ocean ever existed as liquid on the surface, or whether Venus simply never accumulated much surface water to begin with, is still debated. There is one piece of indirect evidence that Venus might once have had more water: the ratio of deuterium to hydrogen in Venus's atmosphere. Deuterium is a heavier isotope of hydrogen, with one extra neutron in its nucleus. Because it's heavier, deuterium is lost to space more slowly than ordinary hydrogen during the escape processes that drain planetary atmospheres. If a planet loses a large fraction of its water over time, the ratio of deuterium to hydrogen in the remaining water rises. The lighter hydrogen escapes preferentially, leaving the deuterium behind in higher relative concentrations. Venus's deuterium to hydrogen ratio is about 100 times higher than Earth's. This enrichment in deuterium is strong evidence that Venus once had significantly more water than it has today, and that this water was lost gradually over a very long period through the same escape processes that continue today at lower rates. Whether the water Venus lost was ever enough to cover the surface in liquid oceans is a question the geological record cannot currently answer. The surface is too young, too reshaped by subsequent volcanic activity, to preserve the kind of evidence. Ancient shorelines, sedimentary deposits, chemically altered rocks that might record a watery past. But the deuterium enrichment tells us that at minimum, Venus had enough water to matter, and it lost it. The absence of a magnetic field is another of Venus's defining features, and it connects to several of the other puzzles the planet presents. Planets generate magnetic fields through a process called the geodynamo, a self-sustaining process of convection in an electrically conducting fluid, typically molten iron in a planet's outer core, converting kinetic energy into magnetic energy. For this to work, you need a conducting fluid in motion, which means a core that is hot enough to remain liquid and convecting, driven by heat flowing from the hot interior to the cooler outer regions. Earth has a geodynamo because its inner core is solid and its outer core is liquid, with heat flowing outward from the inner core into the outer core and then into the mantle, driving the convection that generates the magnetic field. Mars had a geodynamo early in its history, but lost it when its small core cooled below the temperature needed to maintain convective motion. Mercury has a surprisingly active geodynamo, given its small size, probably maintained by the concentration of sulfur or other light elements in its core that lower the melting point and keep the outer core liquid. Venus is the mystery. Its size and density suggest it should have a similar interior structure to Earth, a solid inner core, a liquid outer core, a mantle. It should, in principle, have a geodynamo. And yet it doesn't, or at least doesn't have one producing a measurable global magnetic field. One leading hypothesis is that Venus's core is not convecting effectively, that the temperature difference between the inner core and the outer mantle is too small to drive the vigorous convection needed for a dynamo. This could happen if Venus's mantle is a poor conductor of heat, trapping heat in the interior and reducing the temperature contrast that would otherwise drive core convection. Without plate tectonics to efficiently transfer heat from the mantle to the surface and ultimately to space, Venus's interior may be maintaining a high enough temperature that the temperature difference between the core and the mantle is too small to drive strong convective flow. Another hypothesis connects to Venus's slow rotation. The strength of a planetary magnetic field is influenced by the planet's rotation rate. Faster rotation helps organize the convective flows in the core into the coherent, large-scale patterns that generate an organized dipole magnetic field. Venus's extremely slow rotation may produce only weak, disorganized convective flows in the core that generate insufficient magnetic field to be detectable at the surface. The absence of a magnetic field has practical consequences for the planet's current state. Without magnetic protection, the solar wind has been directly eroding Venus's upper atmosphere for billions of years, stripping ions and accelerating the loss of atmospheric gases to space. This is particularly important for the loss of water, as described earlier. Without magnetic protection, the solar wind can directly pick up ionized hydrogen from the upper atmosphere and carry it away. The rate of hydrogen loss from Venus is measurably higher than it would be with a magnetic field in place. The irony is that Venus's atmosphere is so thick and so massive that even billions of years of solar wind erosion haven't significantly depleted it overall. The atmosphere is not being stripped away fast enough to matter on the timescale of the solar system. It's simply too much gas. But the water that Venus once had was far more vulnerable, being present in much smaller quantities, and its loss has been essentially irreversible. One of the most captivating and still unresolved debates in planetary science concerns whether Venus was ever habitable, whether, at some point in its past, the planet had conditions at its surface that could support liquid water and potentially life. The question is not as obviously answered as it might seem. Current models of planetary habitability based on stellar luminosity alone tend to place Venus's orbital distance right at or just inside the inner edge of the Sun's habitable zone, where the Sun's energy output today would be enough to maintain runaway greenhouse conditions. But the Sun is not constant. It is brightening over geological time, as hydrogen fusion converts mass to energy in its core and the helium ash gradually builds up, causing the core to contract slightly and run hotter. 4 billion years ago, the Sun was about 30% less luminous than it is today. Earth's early climate was cold enough to present its own habitability challenges, the faint young sun problem that climatologists grapple with. But for Venus, a dimmer early sun means less energy input, which means potentially cooler temperatures, which means potentially liquid water could have existed on the surface for a significant period. The question becomes, how long could liquid water have survived on early Venus before the sun brightened enough, or before volcanic outgassing added enough carbon dioxide to the atmosphere, or before whatever water existed was photodissociated and lost to space? Some models suggest Venus could have had surface liquid water for as much as 2 billion years, roughly half the current age of the solar system. Others suggest the planet was too hot, even from the beginning, for liquid water, if it lacked the reflective clouds that would have moderated its surface temperature, or if its initial water inventory was small. The range of estimates is enormous, driven by uncertainty about Venus's early rotation rate, early cloud cover, early atmospheric composition, and early water inventory. If Venus did have surface liquid water for even a few 100 million years, that is long enough, by Earth standards, for life to potentially emerge. Life on Earth is thought to have emerged within a few 100 million years of the planet's formation, based on the earliest isotopic and microfossil evidence. A Venus with warm, liquid water, a reducing or neutral atmosphere, and volcanic hydrothermal systems on its seafloor would have provided many of the same ingredients that produced life on early Earth. This is not an argument that life actually arose on early Venus. It is simply the observation that if the conditions were right, and if they persisted long enough, the same basic chemistry that produced life on Earth could have operated on Venus as well. And then, when Venus's climate deteriorated, as the sun brightened, as the greenhouse effect intensified, as the surface water evaporated and was lost, whatever life might have existed on Venus's surface would have faced an extinction event of planetary proportions. The surface became uninhabitable and stayed uninhabitable. Could any trace of a formerly living Venus survive? Almost certainly not on the surface, which has been repeatedly resurfaced by volcanism, baked at 465 degrees, and processed by the chemically aggressive atmosphere for potentially billions of years. But the upper atmosphere is a different matter. Carl Sagan and Harold Morowitz proposed in 1967 that if microbial life ever existed on Venus, the transition from habitable to uninhabitable might have driven some organisms to adapt to atmospheric rather than surface conditions, surviving in the temperate zone of the cloud layer. And while this is highly speculative, there is no evidence of such organisms and significant scientific skepticism about the hypothesis. It has never been definitively ruled out. The question of life in Venus's clouds must be treated with discipline. It is easy to make it sound more dramatic than the evidence allows. The cloud layer has temperatures and pressures that are not absurd for life, but it also has concentrated sulfuric acid, extreme dryness, strong ultraviolet radiation, and chemistry unlike any stable habitat on Earth. Life as we know it requires a solvent, a source of energy, and chemistry capable of storing and transmitting information. On Earth, liquid water is that solvent. In Venus's clouds, water is scarce and bound into highly acidic droplets. Some microbes on Earth tolerate acidity, and some tolerate dryness, but the combination expected in Venus's clouds is far beyond ordinary biological comfort. Any hypothetical Venusian life would either need biochemical strategies unlike known life, or would need microenvironments in the clouds that are less hostile than the average conditions. This is why many scientists remain skeptical. Skepticism is not closed-mindedness here. It is the correct response to weak evidence and hard chemistry. The burden of proof for life is high, especially on a planet where exotic non-biological chemistry is already expected. A strange molecule is not life. A chemical imbalance is not life. A missing pathway in a model is not life. It is a question, but questions are useful. The life debate forces scientists to study the clouds more carefully. It forces better measurements of acidity, water activity, trace gases, aerosol composition, particle size, and vertical mixing. Even if the answer is no life, the investigation will improve atmospheric chemistry. It will teach us how far from Earth-like conditions organic chemistry can persist, and how to interpret possible biosignatures on exoplanets. Venus is especially valuable because it warns against overconfidence. If we observed Venus from another star system, we might see a rocky planet near the inner edge of the habitable zone, roughly Earth-sized, with a thick atmosphere. Depending on the quality of the data, we might misunderstand it badly. Venus teaches that a planet can look promising in broad categories and be completely hostile in detail. It also teaches that atmospheric gases are hard to interpret without context. A possible biosignature molecule must be understood inside the whole system. Geology, photochemistry, clouds, surface conditions, escape processes, and stellar environment. So the question of Venusian life is not only about Venus. It is a training ground for the search for life elsewhere. It asks how careful we must be before claiming biology, how many non-biological explanations must be tested, and what combination of gases, particles, isotopes, and environmental measurements would actually make a life hypothesis stronger than chemistry alone. That is a mature scientific question. It does not need hype. It does not need fantasy. It needs measurements. Which brings us to the phosphine controversy, one of the most discussed episodes in recent planetary science. In September 2020, a team of astronomers led by Jane Greaves of Cardiff University announced the detection of phosphine in Venus's atmosphere at a concentration of about 20 parts per billion, based on observations with the JCMT telescope in Hawaii and the ALMA array in Chile. Phosphine, a molecule of one phosphorus atom bonded to 3 hydrogen atoms, pH3, is significant because on rocky planets like Venus, it should be rapidly destroyed by photochemical reactions and not be expected to exist in detectable quantities unless it is being continuously produced. On Earth, phosphine is produced almost exclusively by biological processes, by anaerobic microorganisms that generate it as a metabolic product in oxygen-poor environments like marshes and animal intestines. In industrial settings, it can also be synthesized chemically, but there is no known purely abiotic geological process that produces it in significant quantities in the kinds of environments found on rocky planets. The announcement was explosive. If phosphine genuinely existed in Venus's atmosphere at the reported concentration, it would require an explanation, and biology was one possible explanation. Headlines around the world declared that signs of life might have been found on Venus. Scientific discourse was, appropriately, more measured. What followed was a long, complex, and still ongoing scientific debate about the validity of the detection and its interpretation. Multiple groups reanalyzed the same observational data and arrived at different conclusions about whether the phosphine signal was real, how strong it was, and whether the analysis had been done correctly. Issues with the ALMA data calibration were identified that reduced the statistical confidence in the detection. The reported concentration of 20 parts per billion was revised downward in subsequent analyses, with some groups finding no convincing detection at all. The current scientific consensus is genuinely uncertain. Some researchers maintain that a phosphine signal, at some level, exists in the ALMA and JCMT data. Others argue that it is an artifact of calibration errors and data analysis choices. A definitive answer requires more observations with better instruments, ideally including in situ measurements in Venus's atmosphere from a spacecraft equipped to detect phosphine directly. What is also true is that even if phosphine is present in Venus's atmosphere, biology is not the only possible explanation. Researchers have proposed a variety of non-biological mechanisms that could produce phosphine: volcanic activity involving phosphorus-bearing rocks, lightning-driven chemistry, photochemical processes involving sulfur and phosphorus compounds, and others. None of these mechanisms, in current models, is clearly capable of producing phosphine in the quantities originally reported, but the uncertainty about Venus's interior chemistry, atmospheric chemistry, and volcanic processes is large enough that non-biological explanations cannot be ruled out. The phosphine controversy has had one unambiguously positive effect. It dramatically accelerated interest in Venus missions designed specifically to study Venus's atmospheric chemistry in detail. If phosphine exists, we want to know how much, where in the atmosphere it is concentrated, whether its abundance varies over time, and what chemical context it exists in. These are questions that can only be answered with in situ measurements from an atmospheric probe, not from Earth-based radio telescopes or even orbiting spacecraft, but from an instrument physically present in Venus's atmosphere. That is exactly the kind of measurement that upcoming missions are designed to provide. The history of spacecraft at Venus is, ironically, richer than most people realize. In the early decades of the space age, Venus was actually a more popular destination for spacecraft than Mars because its closer average distance to Earth and the generally better orbital mechanics made it somewhat easier to reach on a fuel budget. The Soviet Union in particular made Venus a priority. The Soviet Venera program, running from the 1960s through the 1980s, represents the most sustained campaign of Venus exploration ever mounted. It included 14 spacecraft that successfully reached Venus, of which 10 eventually landed on the surface. The history of the program is a story of progressive learning through repeated failure, each mission revealing new information about exactly how hostile Venus's environment was, prompting redesigns, improvements, and eventually the development of spacecraft capable of surviving long enough to return meaningful data. Venera 1, launched in February 1961, was the first spacecraft aimed at Venus, but contact was lost before it reached the planet. Venera 2 and 3, launched in 1965, also failed to return data from Venus, with Venera 3 crashing into the planet's surface in March 1966, the first human-made object to reach another planet's surface, though it returned no data from the impact. Venera 4, launched in 1967, was the first spacecraft to successfully return data from another planet's atmosphere, transmitting temperature and pressure measurements as it descended into Venus's atmosphere until it was crushed by the pressure before reaching the surface. The data it returned, showing atmospheric temperatures far higher and pressures far greater than most scientists had expected, was the first direct confirmation of just how extreme Venus's conditions were. The discovery that Venus's surface was even hotter and denser than the Venera 4 data implied led to a fundamental redesign of subsequent landers. Venera 7, launched in 1970, was built to withstand pressures of 180 atmospheres and temperatures of 540 degrees Celsius, deliberately over-engineered to ensure it could survive the conditions now known to exist on the surface. On December 15, 1970, Venera 7 landed on Venus and transmitted data for 23 minutes, the first spacecraft to successfully land on another planet's surface and return data. The data it returned confirmed surface temperatures of about 470 degrees Celsius and pressure of about 90 atmospheres. The era of direct measurement of another planet's surface had begun. Venera 9 and Venera 10, arriving in October 1975, were a major step forward. Each carried a lander equipped with television cameras and instruments for measuring the composition and mechanical properties of surface rocks. The images returned by Venera 9 and 10 were the first photographs taken from the surface of another planet, black and white panoramas showing rocky terrain, angular slabs of rock clearly of geological interest, surfaces that showed far less wind erosion than had been expected. The terrain around Venera 9 showed young, sharp-edged rocks consistent with recent volcanic activity. The terrain around Venera 10, about 2,000 kilometers away, showed older, more rounded rocks. Different geological histories at two different landing sites, apparent even from those first crude images. Venera 13 and 14, arriving in March 1982, transmitted color images of the Venusian surface for the first time. The colors were dominated by the orangey-brown tones of the sky and the dark gray-brown of the basaltic rocks, with the overall lighting giving the scene an eerie, reddish quality unlike any familiar landscape. Venera 13's landing site showed flat, plate-like slabs of rock, some with curved edges suggesting they had broken from a larger mass. Venera 14's site showed smoother, more layered terrain. Both landers drilled into the surface and analyzed the composition of the rock, finding basaltic material consistent with volcanic origin, the first direct geochemical analysis of the surface of another planet. Venera 13 survived on the surface for 127 minutes before being destroyed. Venera 14 lasted 57 minutes. These remain the longest surface survivals ever achieved on Venus. Every instrument was designed knowing it had, at best, 2 hours to function before the environment destroyed it. Every scientific measurement had to be planned with that clock in mind. The program also included Vega 1 and Vega 2 in 1985, dual missions that each released a lander and an atmospheric balloon at Venus before continuing to Halley's Comet. The balloons were the first aerial explorers of another planet. They floated in Venus's cloud layer at an altitude of about 54 kilometers, where conditions are relatively moderate, and drifted with the winds for about 46 hours, transmitting data on temperature, pressure, wind speed, and cloud structure. Each balloon traveled roughly 11,000 kilometers during its operational lifetime, carried around the planet by the super-rotating atmospheric winds, before its batteries died. They demonstrated that aerial exploration of Venus's atmosphere was not just possible but productive, and they inspired subsequent proposals for atmospheric missions. The United States contributed to Venus exploration primarily through Pioneer Venus in 1978, an orbiter and 4 atmospheric probes that descended into Venus's atmosphere simultaneously and transmitted data during their descent, greatly expanding knowledge of the atmospheric structure and composition, and through the Magellan spacecraft from 1989 to 1994, which mapped nearly the entire surface with synthetic aperture radar at a resolution high, enough to reveal surface features as small as about 100 meters across. Magellan's mission was extraordinary in its scientific productivity. Orbiting Venus in a highly elliptical orbit that brought it to within about 290 kilometers of the surface at closest approach, Magellan used its radar to illuminate the surface and detect the reflected signal, building up detailed maps of surface topography and surface texture one strip at a time, orbit by orbit. By the end of its primary mission, Magellan had mapped about 98% of Venus's surface, the first time virtually the entire surface of another planet had been mapped in detail. The resulting dataset remains the foundation of Venus geology to this day. When Magellan's mapping mission was complete, the spacecraft was used for gravity mapping, measuring tiny variations in its orbital speed caused by variations in the gravitational pull of different parts of Venus's interior, from which scientists could infer information about the internal density distribution. Then, in its final days, Magellan was deliberately lowered into the upper atmosphere in a sequence of aerobraking passes, gathering data on atmospheric density before eventually burning up on impact. Like Cassini at Saturn, Magellan was destroyed in a deliberate act of planetary protection, ensuring the spacecraft could not contaminate Venus by crashing uncontrolled into its surface. The European Space Agency's Venus Express orbited Venus from 2006 to 2014, studying the atmosphere, clouds, and plasma environment in detail. It provided the infrared data that suggested possible current volcanic activity, measured the hydrogen escape rate, characterized the superrotating cloud system in detail, detected evidence of past liquid water through deuterium measurements, and contributed significantly to understanding the chemistry of the upper atmosphere. Japan's Akatsuki spacecraft, launched in 2010, missed its intended Venus orbit insertion and spent 5 years in solar orbit before a second orbital insertion attempt in 2015 successfully placed it around Venus. Akatsuki studied Venus's atmospheric dynamics for years after its successful orbit insertion, using multiple cameras sensitive to different wavelengths to study the cloud structure, atmospheric temperature distribution, and wind patterns at different altitudes. JAXA completed Akatsuki operations in 2025, closing one of the most important modern chapters in the long-distance monitoring of Venus's atmosphere. One of its notable findings was the detection of an enormous, stationary wave structure in Venus's upper cloud layer, a bow wave shape extending from pole to pole, apparently fixed in position relative to the surface below rather than flowing with the superrotating winds. This structure, about 10,000 kilometers across, is thought to be an atmospheric gravity wave generated by air flowing over a large mountain range on the surface below, an atmospheric imprint of the topography, visible in the clouds 60 kilometers above the surface. The discovery illustrated how surface features can influence the upper atmosphere, even through tens of kilometers of dense cloud. The next generation of missions, Da Vinci, Veritas, and Envision, builds on everything learned from these preceding missions. Each is specifically designed to address the most important questions that previous missions have raised but not answered. The detailed composition of the lower atmosphere, including trace species, the geological history of the Tesserae Highlands, the evidence for current volcanic activity, and the mechanisms of atmospheric superrotation and energy balance. Together, they will transform our knowledge of Venus more profoundly than any generation of missions since the Venera program. 3 major Venus missions are currently in development or approved. NASA's Da Vinci, Deep Atmosphere Venus Investigation of Noble Gases, Chemistry, and Imaging, is planned to send a descent sphere into Venus's atmosphere, measuring atmospheric composition as it descends through the cloud layers and the lower atmosphere, down to near the surface. Da Vinci will be the first probe to directly sample Venus's atmosphere since the Soviet Venera program, and its instruments will be capable of detecting phosphine and other trace species at far better sensitivity than Earth-based observations. It will also carry cameras capable of imaging the surface in the infrared during the final portion of the descent, targeting one of Venus's ancient Tesserae Highland regions. NASA currently lists Da Vinci with a tentative launch in 2030. NASA's Veritas, Venus Emissivity, Radio Science, NSAR, Topography, and Spectroscopy, is an orbiter designed to map Venus's surface at far higher resolution than Magellan, using synthetic aperture radar capable of resolving features as small as about 30 meters, and to measure the surface composition using infrared spectroscopy at wavelengths that penetrate the clouds. Veritas would provide the most detailed global surface map of Venus ever made, resolving geological features at a scale comparable to medium-resolution satellite imagery of Earth. It would also search for evidence of current volcanic activity by detecting changes in the surface between repeat radar passes. Veritas faced budget challenges that delayed its schedule, and NASA currently lists the mission as launching no earlier than 2031. The European Space Agency's Envision mission is planned for launch in November 2031. It will orbit Venus and study its surface, subsurface, interior, and atmosphere with radar, spectrometers, and radio science, complementing Da Vinci and Veritas with additional measurements of atmospheric composition and volcanic history. There is another reason Venus missions matter now. They are trying to answer old questions with modern instruments. The Venera landers were heroic, but they were limited by the technology of their time and by survival measured in minutes. Magellan revolutionized Venus geology, but its radar resolution and instrument suite were products of the late 20th century. Venus Express and Akatsuki transformed the study of the atmosphere, but neither was designed to solve every question about surface composition, deep atmospheric noble gases, or active geology. The next missions are not simply repeating old exploration. They are returning with specific questions sharpened by decades of uncertainty. Da Vinci's descent sphere is designed to do something no orbiter can do: directly taste the atmosphere from the top of the clouds downward. Remote sensing can infer composition, but a probe descending through the atmosphere can measure noble gases, isotopes, trace chemicals, pressure, temperature, and winds in place. It can build a vertical profile of the atmosphere, connecting the upper cloud chemistry to the deep lower atmosphere. It can test whether the atmosphere preserves evidence of ancient oceans, intense escape, or unusual volcanic history. Veritas is designed to make Venus geology modern. Magellan gave us a global map, but a new radar mission can map with better resolution, better topography, and repeat past methods that can detect deformation. It can search for active volcanoes not by inference alone, but by comparing the surface over time. It can measure how the crust responds to internal heat. It can help decide whether Venus has an active interior, a squishy lithosphere, regional tectonics, or ongoing resurfacing. Envision will complement this by connecting multiple layers of the planet: surface, subsurface, atmosphere, and interior. Its radar and spectroscopic measurements can look for volcanic and tectonic processes, while radioscience can help refine gravity and interior structure. A mission like Envision is important because Venus's problem is not located in one place. It is not only in the clouds, not only in the rocks, not only in the core. Venus is the result of coupling between all of them. Together, these missions could finally let scientists compare Earth and Venus with the precision the comparison deserves. Not in vague terms like Earth's twin, but with measured differences. How much water was lost, how much carbon dioxide accumulated, what the crust is made of, whether volcanoes are active now, how fast the atmosphere moves, whether tesserae preserve ancient crust, and whether the cloud chemistry contains unknown processes. This is why Venus is entering a new phase. For decades, Mars received more attention because it had ancient river valleys, accessible surfaces, and a clearer astrobiological narrative. Venus seemed too hostile and too difficult. But the questions Venus asks are now impossible to ignore. How do rocky planets lose habitability? How close to a star is too close? How do atmospheres evolve when oceans disappear? How does volcanism affect climate without plate tectonics? How should we interpret Earth-sized exoplanets near the inner edge of habitable zones? Venus is no longer just the bright object in the evening sky. It is a key to understanding rocky planets as a class. Together, Da Vinci, Veritas, and Envision represent the most concentrated period of Venus exploration since the Venera program. They will address many of the fundamental open questions about Venus: its volcanic history, its current geological activity, its atmospheric chemistry including the phosphine question, its past habitability, and the mechanisms responsible for its divergence from Earth. Beyond these approved missions, there is growing discussion of more ambitious future Venus exploration. Long-lived surface landers capable of surviving on the surface for days or weeks rather than hours, enabled by high-temperature electronics and advanced thermal management. Aerial platforms floating in the cloud layer at the temperate altitude where conditions are most manageable, and eventually sample return missions that would bring Venusian material back to Earth for analysis. The technical challenges are formidable. The combination of high temperature, high pressure, and chemical corrosion from sulfuric acid makes Venus's surface the harshest environment in the solar system for spacecraft, more challenging even than the outer planets at extreme distances. But the scientific case for better understanding Venus is sufficiently compelling that the community has consistently prioritized it, and the next decade of missions will dramatically expand what we know about a planet that has been hiding in plain sight for thousands of years. There is a broader perspective on Venus that deserves attention. What Venus means not just as a nearby planet, but as a cautionary example for understanding planetary climate. In recent years, the term Venus syndrome has entered the vocabulary of climate science, describing the possibility of a runaway greenhouse effect on Earth triggered by sufficient accumulation of greenhouse gases. The scientific consensus is that human-caused climate change on Earth, while serious, is not currently on a trajectory toward a true runaway greenhouse effect in the foreseeable future. Earth is too far from the Sun, and its feedbacks are sufficiently different from Venus's for that to be a near-term risk. Earth's distance from the Sun means that even significant warming would not reach the threshold needed to evaporate all of the world's oceans and trigger an irreversible runaway. But Venus illustrates something more subtle and more immediately relevant. It illustrates that planetary climate is not infinitely resilient. It illustrates that the carbon silicate cycle that keeps Earth's temperature regulated depends on plate tectonics and liquid water and the particular architecture of Earth's climate system, and that if those systems are disrupted, the regulatory mechanism breaks down. It illustrates that a planet can reach a state from which recovery is impossible on any timescale relevant to life, not because of any dramatic external event, but because of the slow accumulation of greenhouse gases over geological time interacting with a slow reduction in the feedbacks that would otherwise have moderated it. Venus and Earth are not simply two different planets. They are two possible futures for a rocky world in the inner solar system. Two outcomes that started from nearly identical initial conditions and diverged over billions of years because of a combination of differences in orbital distance, water inventory, rotation rate, and geological history. Understanding which factors were decisive and what margins separated the two outcomes is directly relevant to understanding how stable Earth's climate is and what kinds of perturbations it can absorb before its regulatory systems are strained beyond their capacity. Venus doesn't offer a simple moral or a straightforward lesson. The processes that made Venus what it is operated over hundreds of millions to billions of years and involve factors: the initial inventory of water, the role of early impactors, the trajectory of the early sun's luminosity, that were in many ways outside any living thing's control. Venus is not a story of a planet that did something wrong. It is a story of physics applied to two similar starting points, producing vastly different results. The physics was the same on both planets. The outcomes were not. The exoplanet connection may be the most important reason Venus matters beyond our solar system. Astronomers have now found thousands of planets orbiting other stars, and many of them are close to their stars. Some are rocky, some are larger than Earth. Some receive more stellar energy than Earth, but less than Mercury. Some may be Venus-like in ways we cannot yet prove. From a distance of many light years, a Venus-like world and a potentially habitable Earth-like world may both appear as small rocky planets in similar broad categories. The difference may be hidden in the atmosphere. This creates a serious observational problem. A planet's radius and mass are not enough. Venus and Earth are similar in size, but one is habitable and the other is not. Distance from the star is not enough either. The habitable zone is a useful concept, but it is not a guarantee. Rotation, water inventory, atmosphere, clouds, volcanic history, stellar activity, and interior evolution all matter. Venus is the local example that proves the danger of oversimplification. When future telescopes study the atmospheres of Earth-sized exoplanets, they may look for carbon dioxide, water vapor, oxygen, ozone, methane, sulfur gases, aerosols, and cloud properties. Interpreting those signals will require models. Those models must be tested against real planets. Earth is one test. Mars is another. Venus is the crucial hot inner edge test. Without understanding Venus, we risk misunderstanding worlds that may be common around other stars. A Venus-like exoplanet might have a thick carbon dioxide atmosphere, high clouds, little water, and extreme surface temperatures. But from far away, the surface would not be visible. The clouds might reflect starlight strongly, making the planet look bright. Its radius might look inviting. Its location might seem near the habitable zone, depending on the star. Only careful atmospheric measurements could reveal the truth. This is why the phrase, Earth's twin, is both useful and dangerous. It is useful because it emphasizes the shared starting point. It is dangerous because it can make similarity sound deeper than it is. Venus is Earth's twin in size, mass, and rocky nature. It is not Earth's twin in climate outcome. For exoplanet science, that distinction is everything. Studying Venus helps define the inner edge of habitability. It helps answer how much sunlight a rocky planet can receive before water loss becomes irreversible. It helps explain how clouds can either cool a planet by reflecting sunlight or help maintain a hot lower atmosphere. It helps determine which gases indicate active volcanism, which indicate water loss, and which might be confused with biological processes. It gives context to the search for life by showing what a lifeless but chemically active rocky planet can look like. In this sense, Venus is not only a neighbor, it is a calibration point for the galaxy. That, ultimately, is what makes Venus worth studying so carefully and worth understanding so precisely. Not as a warning in any simplistic sense, but as a natural experiment. A controlled test, run at planetary scale, over billions of years, of what happens to a world like Earth when key parameters shift. The data from that experiment are recorded in Venus's surface chemistry, atmospheric composition, and thermal state. Reading that data precisely enough to understand exactly what shifted, and when, and by how much, and with what consequences, that is the work of the next generation of Venus missions. Venus is the most Earth-like planet we know, and it is also the most hostile to Earth life. That contradiction sits at the center of nearly everything that makes Venus scientifically important, and it sits, bright and patient, in the sky every evening, waiting to be understood. Venus is often visible if you know where to look. In the western sky after sunset, it outshines everything, a steady, brilliant white point that does not twinkle the way stars do, because it is close enough to show as a tiny disk rather than a pure point source, and its disk averages out the atmospheric distortion that makes stars shimmer. It's the brightest non-lunar object in the sky. It has been watched, named, and wondered about by human beings for thousands of years. What those human beings were watching, without knowing it, was a catastrophe in slow motion. A world slightly closer to a young star than was quite safe, with slightly too much carbon dioxide and slightly too little water, and no plate tectonics to regulate the carbon cycle, and a magnetic field that faded as the interior cooled, and a slow spiral into conditions that nothing on Earth could survive. It all looks very peaceful from here. Bright, steady, beautiful in the evening sky. The ancient observers were right to name it after their goddess of love. It is beautiful, in its way, in the distance. What they couldn't know is what that beauty was concealing. 465 degrees, 90 atmospheres of pressure, sulfuric acid clouds, and a surface that has been trying to tell us something for the entire history of science, waiting patiently for instruments good enough to hear it. Those instruments are coming. If the planned missions proceed, the 2030s should transform Venus science more profoundly than any period since the Venera and Magellan eras. We'll know whether phosphine exists in its clouds. We'll know whether it is volcanically active today. We'll know, in better detail than ever before, what its surface is made of and what processes have shaped it. We'll understand better how it diverged from Earth, and what that divergence means for understanding our own planet's past and future. Until then, Venus remains where it has always been, close, bright, and difficult to understand. It is not a mythic goddess, not a simple warning, and not merely Earth's failed twin. It is a complete world with its own history, its own physics, and its own unanswered questions. A planet almost like Earth in size. A planet nothing like Earth in outcome. A furnace hidden behind white clouds, shining calmly in the sky.